Hello, this is AIMET 104, lecture recording week 11.2. So last class we started on the concept of probability, and I'm sure a lot of you are very familiar with these concepts. So two things to note is that the probability, so probability, let's say, of an event E is denoted as probability of E, and two things is that the probability is always in between 0 and 1. And another thing is that if you add all the probabilities, so the sum of all let me quickly, okay, sorry about that. Sum of all probabilities of simple events is equal to 1. So those are the two rules that would qualify something to be a probability assignment. Before we ended the last class, we went over this concept of independence. So and independent events, even though we went over last time, is going to be used a lot today. So I'm going to redefine it. I'm going to briefly define it. So if you want more explanation, you should go back to last class. So two events are said to be independent if the probability of one event does not affect the probability of the other, or vice versa. So, and when event, let's say A and B are independent, the probability of A and B happening at the same time would be the probability of multiplied by the probability of B. And this is called the multiplication principle. So when it comes to independent probability, it means that two events are not linked to each other. So for example, if you are rolling a die twice in a row, or if you are flipping a coin twice in a row, and things like that, it's not going to, so the first result will not affect the result of the second, and or vice versa. And those are called the independent events. We are not going to go over dependent events in this class, and dependent events can get very tricky and it gets very computation heavy, but so we're only going to look at independent events. So when you are given problems, it is safe to assume that even though I'm sure you are able to just read and understand that two events are independent, it is also safe to assume that all the events that we are given in this problem are independent. So let's actually do an example of an independent event. And this is going to be a very advanced example, sorry. So let's say, so remember last time we did an example on rolling a dice. So if you say we had an event defined as when suppose you roll a pair of dice and say that the event is defined as at least one of the dice comes up 1. and suppose, and obviously the complement event here is the none of the die comes up 1. And last time we looked at if this is a winning condition and if this is a losing condition. We have also seen that the probability of E and F are complements. Each other. So in other words, we concluded that the probability of E plus the probability of F has to equal 1. So the first time, so when we were solving this problem, the way we solved, so the way we solved last time, we simply found all the different ordered pair. So for example, we had 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 2, 1, 3, 1, 4, 1, 5, 1, and 6, 1. And we could see that there are 11 elements in this event. So out of 36 possible outcomes, we know that the probability of the E is 11 over 36. And because it is complement with F, we also saw that probability of E plus the probability of F equals to 1, which means that the probability of E, which we know as 11 over 36, plus the probability of F equals to 1. So we concluded the probability of F in this case is 25 over 36. So that's actually how we computed last time. In this case, it was not that difficult, but when you're counting all these different possibilities, it's possible that you may lose one or two. So we're now going to solve the same problem, but now using the independent event and its multiplicative property. So now, so let me say Now, let F1 denote the event. So let's say the first die does not come up 1. And let's say F2 is the second die does not come up 1. We should be able to see that that the event F itself is simply defined as F1 and F2 occurring at the same time. I know this wording can be very confusing, but let's step back and look at this. So event F, the event of losing, is simply saying that none of the die comes up 1. So the first die and second die, they both should not be 1. When the first die and second die are not 1, it means that the first die is not 1 and the second die is not 1. It sounds very straightforward and trivial statement, but this is important because now that you can separate the two events, so the outcome of the first die and the outcome of the second die, we can separate it into two different events, and we can denote the F1 to be the outcome of the first die and F2 be the outcome of the second die. And since in this case we're more interested in the probability of losing, we can simply say the first die does not come up 1 can be the first event, and the second die does not come up 1 can be the second event. And as you can see, if none of the die comes up 1, it simply implies that F1 and F2 are happening at the same time. And as we can see, so since the outcome of each die is independent of the outcome of the other, we can simply say that this implies that F1 and F2 are independent events. Then we can simply see that the probability of F is simply the probability of F1 and F2 happening at the same time. And I'm sure we can all agree with that by now. And this means that by multiplication principle, we can simply say that this is the same thing as probability of F1 multiplied by probability of F2, And as you can see, the probability of F1, the first die does not come up 1, is simply out of 6, 1, 2, 3, 4, 5, 6. The outcomes that is not 1 is 2, 3, 4, 5, and 6. So hence, we know that it's a probability of F1 is simply 5 over 6. And similarly, probability of F2 is also 5 over 6 because there's only one out of 6. Then simply by multiplication principle, we can do that 5 over 6 multiplied by 5 over 6. And hence, this is 25 over 36. And since the event E, in other words, the winning event is the complement of the event F, we can simply say that probability of E and probability of F equals to 1, and hence we can simply plug in 25 over 36 for F, and hence you actually end up with the probability of E, so the probability of winning this game is 11 out of 36. So as you can see, we actually concluded the same result. So we actually came to the same results as simply counting all these outcomes. So some of you might be thinking using the independent event may be a little too counterproductive when it's easy enough to simply just count all these things. But when it comes to something big, so when it comes to 3 die, 4 die, so if you are rolling many more dice, it's going to be very time consuming, and it's going to be very hard to track down every single one of these numbers. So without a further ado, I'm actually going to do an example like that. So let's do an example with, let's say, 4 different dice. So example. So imagine you are rolling a regular die 4 times. If at least one of the dice comes up 1, you win the game. And let's say the probability of E is, the event E is simply you win. In other words, at least one of the die comes up 1. And in this case, let's say you want to find the probability of winning this game. So in other words, out of 4 ordered pairs, so for example, if you have 1, 2, 2, 2, that's a winning outcome. If you have 3, 4, 6, 1, that's also a winning pair. So you are to find all the possible outcomes that will have at least 1 in this role. So if you proceed to calculate all this, count all these outcomes, it's going to be very, very time consuming. When it comes to 2, when we're rolling 2 dice in the previous example, we only had to count up to 11. And now it's going to be hundreds and hundreds. And if you want to actually go ahead and count them, please do so. But I'm going to try to solve this problem using the independent events. So let's actually denote the probability of, let's actually define some other event. So let's say define F to be the event that you lose. So F is a losing scenario. In other words, F is defined as none of the die comes up 1. And none of the 4 die comes up 1. In the previous example, we could see that we were able to divide the losing scenario into 2 different events. And in this case, we're going to do the same. But instead of 2 different events, we're going to do the 4 different events because we're going to look at each die separately. So now define as such F1 to be first roll is not 1, and F2 is the second roll is not 1. F3 is third roll is not 1. And lastly, F4 is fourth roll is not 1. As you can see that each individual roll, F1, F2, F3, and F4, are independent of each other. The result of the first roll does not affect the result of the second roll. The probability of getting any number for each event does not affect the other. Then we can simply calculate that since F1, F2, F3, and F4 are independent of each other. Let's say independent events. We can simply see that the probability of F, meaning that none of the die comes up 1, is simply defined as the probability of F1 and F2 and F3 and F4, meaning that if none of the die comes up 1, it implies that first die is not 1, second die is not 1, and third die is not 1, and the fourth die is not 1. And since it's independent by multiplication principle, we can simply say the probability of F1 multiplied by probability of F2 multiplied by probability of F3 multiplied by probability of F4. And since each F1, F2, F3, F4 is 5 out of 6, and we know that from the previous example, I'm not going to write it there. So simply each probability here, we have 5 out of 6 because there's only one multiplied by 5 out of 6, multiplied by 5 out of 6, multiplied by 5 out of 6. And simply this is, I'm going to write it in decimal, it's going to be 0.482 approximately. So this 0.482 is the probability of losing. And then finally, since event E and F, in other words, winning and losing, are complementary events, in other words, they are complementing each other. We have this drawing pad is acting up a little bit. We have probability of E plus the probability of F equals to 1. And since we know that the probability of losing is 0.482, we can simply say that the probability of E plus 0.482 equals to 1. And hence, we can find that the probability of winning is 1 minus 0.482, and that is simply 0.518. So as you can see, in this case, even though this took a lot of time, there is really no other way to find this number other than using the independent event. I mean, sure, you technically can find all these different outcomes, but it's actually going to be hundreds of different outcomes. And in the process, you're bound to miss a few, and you're going to end up with a wrong answer. So even though this may seem a little too complicated and seem counterintuitive, this is actually the better way and more correct way to solve these type of problems. So we're actually done with the chapter 16.3, but before I go over to the next chapter, I actually want to do one special example. I want to put it in here because it's regarding probability. It's not necessarily independent probability or anything like that, but this is a fun problem. And this is called the Monty Hall problem. And this is also a paradox. Some of you may already know this problem, some of you may not. This is actually a very popular problem, and I'm actually not going to solve the problem here. I'm only going to present it, and I am going to let you think about it. Normally, if you were having in-class meetings, I normally put this up on a class discussion, and we would talk about what students think about each, like what each people think about the outcome. But because we cannot do that right now, I'm simply going to present the problem, and I want you to think about it. I'm going to reveal the answer later in the course. I know we only have maybe a couple more weeks to go, but I'll find a time to do so. And also, if you really want to look it up, I'm sure there are a lot of YouTube videos that's explaining this type of problems. So this is a very famous paradox. In other words, it's not intuitive. So let's say you are a contestant in a TV show, and you have to choose one of the three doors. To win either a fancy car, whatever car it is, and it's behind one door, or a goat. In other words, you lose in this scenario, behind two other doors. So simply it's like this. So let's say this is a door. And for the sake of the problem, I'm going to say this is door 1, door 2, and door 3. And behind one of these doors, you do not know what's behind the door, but behind one of the three, there is a fancy car. And behind the other two, there are a goat in each. So simply, obviously, your goal is to choose the car without knowing what's behind it. So simply, it's a probability game. So in this case, we know that the winning probability for now, we can say it's 1 out of 3 because there's one door of winning, 2 doors to lose. And that's simple. But now, so without the, and you're in a TV show and the TV show host knows where the car is. And suppose they opened one door that you did not choose. So suppose this is an example. So it's a scenario. Suppose you chose a door, and let's say door number 1, and this is just for the sake of the problem. You could have chosen 2 or 3, it doesn't matter. And here we know that your winning probability, or in other words, the probability that the cars behind the door 1 is 1 out of 3. And now host opens, let's say, the door number 3, and there is a goat behind it. It could have been any door, but anything that you did not choose. So if you chose 2, host would have opened either 1 or 3. If you chose 3, host would have opened 1 or 2. But because host knows where the goat is, where the car is, they simply opened the door that has a goat behind it, and that's the entire point of this. And the host gives you the option, and offers you the option of switching to the other door. In other words, in this case, switching to number 2, because that's the only door that's not revealed, right? Do you take it or not? So that's the whole problem. Should you switch the door, or stick to what you chose? So this is the whole problem. So in other words, let me just explain it without writing. So you're given 3 doors. So you're given 3 doors that's not revealed. Behind one of the doors, there's a car. Behind the rest of 2, there are goats. In other words, you lose. And you get to choose one of the doors. So in this scenario, let's say you chose 1, but you could have chosen 2 or 3, but it doesn't matter. And now the host opens the door revealing a goat. Opens the door, one of the doors that you did not choose, and reveals a goat. And he can do this because he knows where the goat is. And after then, you are offered a chance to rethink and switch your decision. So now the door 3 is open. You can either stick to your initial choice of door number 1, or you can switch to door number 2. In this case, should you do so or not? And that's the whole point of this problem. Or, I mean, does it really not make any difference? That's, I guess, another way to go about this. Usually, a lot of the students do think that it doesn't make any difference. Some students think it's better if you do not choose. But this is not about instinct. This is not about instinct. This is purely about probability, and you gotta look at this in a very mathematical sense. Your instinct is just an instinct. There is no value to having a feeling of, oh, I feel like something is going to be behind this door. Has no value other than just words. So here, just purely looking at this problem from the probability standpoint, should you choose to stick with your initial decision, or choose to switch your decision? So I'm actually going to end the class here. I'm not going to reveal the answer. The answer will be revealed sometime in the future, probably next class, if not some other time. But do think about this. And if you are really interested, if you're really keen to find out, you can always search YouTube or just Google. And there are a lot of different resources that explain this really well. And if you want to discuss and talk about this problem, and if you have a very clever idea, you can always contact me through email. So, as I said, I'm going to end the class here. So thank you for joining the class, and I hope you have a great rest of the day.